Hello and welcome to Lecture 2 of Gauss's Law in Phys 1204. In this lecture we're going to meet a new concept, electric flux. And this is one of only several types of flux that we'll encounter through the course. So before I get to electric flux, I'm going to start with the general idea of what a flux is. Let's start by thinking about a marching band. So here's a top view of a marching band, and they're all walking in formation with some velocity v. And let's say that there's one of those inflatable archways, so that the area enclosed by that archway in the top view is just this line here. We can now talk about how many musicians per unit time march through this archway. Well, clearly, if they march faster and keep their same formation and so on, the number of musicians walking through that archway per unit time is going to increase. So we're going to define this quantity the musician flux, which is the number of musicians per unit time marching through our archway. And it clearly must be proportional to the speed that they're marching at. But also, if we use a double-width archway so that the whole marching band can go through, that's also going to increase the number of musicians per unit time passing through the archway. And so our musician flux must be proportional both to the speed of the musicians and the area of the archway. But there's one more thing that it depends on. Here's a group of musicians who are walking quite close together, and here's a different group who are walking farther apart. And they're both walking through archways of the same area. And if they're walking with the same speed, then you can see that there will be more musicians per unit time walking through the archway in this group than in this group. And so the musician flux must also depend on the musician density, how many musicians per square meter there are. And so overall, the musician flux must be proportional to the musician density, the speed that they're marching at, and the area of the archway that they're marching through. Let's apply the same idea to a more physicsy idea. So here is a floor plan of a house. You can see some doors and windows, and these are velocity vectors of air currents. And as an engineer designing, say, the ventilation system of the house, you might be interested in the rate at which the air is flowing through this doorway. So the doorway has some area A, and clearly the flux of air through it must depend both on the speed of the air going through the door and the area of the doorway. And the units will tell you what this is a measurement of. That speed is in meters per second and the area is in square meters, and so overall this flux is in cubic meters per second. So it's clearly telling us about the volume of air per unit time that is flowing through the doorway. Perhaps we don't want volume per unit time. If instead we wanted mass per unit time, all we would have to do is multiply by the density of the air, because that's in kilograms per meter cubed, and now when you multiply it by the air volume flux, you're going to get a mass per unit time of air flowing through the doorway. Note that just like the musician flux that we saw previously, this flux is proportional to a density and a speed and an area. In the case of air volume flux, if the velocity vectors of the air are perpendicular to the area that we're thinking about, then the flux really is just the speed times the area. But notice if you have an area that's lying down so that the velocity vectors are parallel to it, clearly no air is flowing through that area, and so now the flux is zero. And in some intermediate case where this area is neither perpendicular nor parallel to the velocity vectors, there's got to be some slightly more complicated relation. It's clear that the flux has to be less than VA, where VA was what it was when the area is perpendicular to the vectors, and if you think about a little bit of trigonometry, you can probably see what the relationship has to be. The area we're thinking about doesn't have to be a real area like the area of a window or a door or an archway. It can be an imaginary area, and most of the time when we're talking about flux, that's what it is. An imaginary area is something like the official strike zone in baseball. There's no frame built around it, but we can still talk about this area and whether or not a ball has gone through it. Now let's apply this same idea of flux to electric fields. And we're no longer going to be talking about the flow of some material or some number of objects like musicians through an area, because an electric field doesn't represent anything moving. What we're going to be talking about instead as electric flux is the number of lines, electric field lines, passing through an area. So let's compare this area A1 and this area A2, and they're the same amount of area. But note that the flux through A1 is 9 lines, and the flux through A2 is 3 lines. But they're the same area. The reason that the flux through A1 is larger is that the electric field is stronger where A1 is, and remember that the strength of the electric field is proportional to the density of field lines. Note, it's important that it's proportional to, not equal to. It doesn't make any sense to talk about it as being equal to, because the number of lines we draw out of each charge is arbitrary. If I divide the number of lines coming out of or into each charge by 3, now the number of lines through A1, the flux through A1, is only 3. And the flux through A2 is now 1. But they've both decreased by the same factor. So it's important to remember that it's proportional to, because the number of lines itself is arbitrary. So an electric flux has to be proportional to the electric field strength, because that's the thing that's proportional to the line density, and to the area that we're talking about the lines passing through. And this is a measure of the number of E-field lines passing through a surface. Again, the electric flux has to have some angle dependence, which we'll look at in detail in a later lecture. But clearly, for a given field strength and a given area, the largest flux occurs when the surface is perpendicular to the field. If we just take that same area and tip it from that, clearly fewer lines pass through the surface, and so we see that the flux is reduced if the surface is not perpendicular to the field. The surfaces I've been considering so far have been open surfaces, but with electric flux, it's going to turn out that we're most concerned with closed surfaces, because the flux through closed surfaces has certain useful properties. What do I mean by a closed surface? Well, let's say we build a box around this charge. That is now a closed surface. It means that it is enclosing some volume of space, and in this case, that volume of space happens to contain a positive charge. The key thing that defines it as a closed surface is that there is no way of getting from the inside of the surface to the outside without passing through the surface. Now notice that there are E-field lines which leave the positive charge. By definition, there have to be E-field lines leaving the positive charge. And since there are no negative charges nearby, all of those lines have to go out to infinity. Well, by definition, infinity has to be outside the surface, and so every one of those lines that leaves the positive charge must pass through the surface. Notice that the truth of that statement doesn't depend on the shape of the surface. Because the charge is inside the surface, every line that leaves it must get to outside the surface, because they have to all head out to infinity. They have to pass through the surface. And so if we replace this cubic surface with a spherical surface, the lines all still must pass through it. And even if we displace the spherical surface over to one side, as long as the charge is still inside the surface, all of those field lines must still pass through the surface. However, if we keep shifting the surface to the side, eventually the situation changes. Once the charge is no longer inside the surface, now there's only one field line that passes through the surface. But notice that it enters on one side of the surface, and it exits on the other side. And in fact, it must, because the only place a field line can terminate is on a negative charge, and there's certainly no negative charge inside that surface. And so if a surface contains no charge, all lines that enter the surface must also exit it. On the other hand, if the surface contains a negative charge, then because lines have to end on negative charges, lines have to enter a surface that contains a negative charge. Because lines can enter and exit surfaces, and the two situations are somewhat different, it's convenient to define the flux through a closed surface as the lines exiting minus the number of lines entering the surface. So with that definition, now you can see that in this picture with the positive charge inside the surface, the electric flux through it is +6. Whereas for this case, where there was 0 charge inside the surface, the flux is 0. And for this case, with the negative charge inside, the flux is -6. The +6 and the -6 are simply because I have arbitrarily decided to draw 6 lines per unit charge. And you can now see that the flux through a closed surface has to be the number of lines per unit charge times the quantity of enclosed charge. Here's an example with more than one charge. So this is a dipole, and notice I've drawn it in 3 dimensions, and I've drawn 6 lines per unit of charge. And if you look at this surface, which is surrounding the positive charge, there are 1, 2, 3, 4, 5, 6 lines leaving it. And so the electric flux is 6 lines. Note that in fact electric flux will have units, but we'll talk more about the units in a later lecture when we're using the flux to calculate something. This is the 3-dimensional picture, but we more often draw pictures like this in 2 dimensions. So here's a different picture of a dipole in 2 dimensions. Note that this time I've drawn 8 lines per charge. Remember that the number of lines per unit of charge is arbitrary, and so the fact that I've drawn 6 here and 8 here isn't meaningful. And again, you can see now that this has 8 flux lines going through it. If we instead have the surface around the negative charge, in this case there are 1, 2, 3, 4, 5, 6 going in, and so the flux is -6, and here we have 8 going in. And one more possibility with this diagram is to have a surface that surrounds both charges. Now note that there are 1, 2, 3, 4, 5 out, and 1, 2, 3, 4, 5 in, for a total flux of 0, which makes sense because the total enclosed charge is 0. And similarly, this one also has a total enclosed charge of 0, and you can verify that the flux is also 0. This rule for the number of field lines passing through a surface can be used in several ways. As we'll eventually see, we can use it to determine electric field strengths. But another way we can use it is that if we know something about the electric field, we can often use this rule to determine how much charge there is in some location. So, try out this question to see if you understand that idea. You have all the information you need in this diagram, along with the rules we've just learned about numbers of field lines passing through a surface, to figure out what the total charge is inside the dashed purple box. This positive charge here has a total charge of Q. And so whatever's in here is going to be some multiple of Q. You just need to figure out what multiple.